We've already talked a little bit about doing mass percent of an element in a compound. So in order to talk about empirical formulas, we need to remember to do that. So this is part of our concept here. So let's take a second here and look at the compound that has the chemical formula C6H12O6. In this particular case, I'm talking about glucose, which is one of our familiar sugars. So take a minute and calculate the mass percent of each of these elements. So we need the mass percent of the carbon, the hydrogen, and of the oxygen. So go ahead and pause the video and calculate that. If you need a little refresher, go back to the video where I talk about mass percent and just go ahead and watch that again first. All right, so hopefully you did this calculation and you found that in this compound we have 40% carbon by mass and 6.71% hydrogen by mass and 53.3%. I guess I need another significant digit, right? Okay, so this happens to be 0, 0. And this one happens to be 2, 8. And now we have the same number of decimal places. Now notice that in this particular case, this doesn't add up to exactly 100%, and this is just a rounding issue that if we take it out to the next decimal place, then all of these will add up to 100%. So when you calculate mass percents, you may find that not every single compound, it adds up to exactly 100%, but it should add up to pretty close. So within rounding, I would say within one decimal place, it should do this. So why am I bringing up mass percent again? Well, before people knew very much about chemical formulas, before they knew very much about atoms, one of the things that they could do was they could figure out what the percent of each compound was, what the percent of element was, based on mass. And so this was something that they could do by various means. Combustion, they could react things with other materials and then look at mass change in their reaction. So there were a number of different tools. And so this concept of doing mass percent is still useful when we are figuring out what compounds are in modern times. So if you don't know what the chemical formula of something is, mass percent is a place to start. And what we can do with mass percents is we can get something called the empirical formula. And the empirical formula is the simplest ratio of the elements in a compound. So let's look at this compound C6H12O6. If I'm talking about the simplest ratio of each of these elements, I'm talking about dividing out the coefficients here into their least common denominator. So what's the number? Not the denominator, that's the wrong term. Into their least common multiple. So we're dividing out the least common multiple to make these the smallest ratio possible. So look at the 6 and the 12 and the 6. What numbers can divide into all of them? And what's the biggest number you can divide into all of them? Hopefully it shouldn't take you too much to realize that we can divide 6 into all of these. And if we divide 6 into all of these, then we're going to get C1H2O1. Or, we would mostly write this as CH2O. And when people first started looking at different sugars, this was actually where they were at. They could look at this C, this carbon, and this H2O. And they knew that water was H2O in terms of the elemental ratios for it. And so this is actually where the term carbohydrate came from. Because they looked at this and they said, well, it's got a carbon, so carbo, and it looks like it has water, so hydrate. Now, the H2O does not actually connect to a carbon in a way that looks at all like water. So this is very misleading, but this is in fact where that name comes from, and it still persists. And so it's kind of fun to find out about where some of these terms come from. Okay, so for C6H12O6, this is the chemical formula, and sometimes we also call it the formula unit. And CH2O would be the empirical formula for it, because that reflects the smallest ratio of each of the elements for this compound. But you would have to multiply all of them by 6 to get to where we finally were. So let's look at a couple of other examples of chemical formulas versus empirical formulas. So let's look at hydrogen peroxide. Hydrogen peroxide has the chemical formula H2O2, and of course we would name it differently. We would call it dihydrogen dioxide if we were using our naming rules for covalent compounds. So this would be the chemical formula. Okay, so this is a fairly simple compound, H2O2, but when we look at the empirical formula, it's even simpler. So what's the ratio? Yeah, you can divide a 2 into both of these. So it would be just H1O1, and of course we don't usually write the 1 for these ones. Okay, so I think you probably have a pretty good sense for what the chemical formula is and what the empirical formula is. And sometimes you will end up with compounds where the chemical formula and the empirical formula, if you work them out, they are the same. So, for example, if we look at methane, it's got 1 carbon, it's got 4 hydrogens. There's no smaller ratio that we can find that's going to give us this 1:4 ratio. And so in this case, the chemical formula and the empirical formula are the same, and that sometimes happens. So how can we know if it's going to happen? Well, the simplest way for us to know is for us to compare the molecular weight, if we happen to know it, of the chemical formula, or, if we happen to know what the compound is, and the molecular weight of the empirical formula. So if you look at HO, the molecular weight of the empirical formula would be 1.0079 plus 15.999, so about 17 grams per mole. And this is never going to stand as a compound by itself for reasons that you'll understand later. So you always, if you have an H and an O, it's going to be part of something else. Just like the OH minus ion, for example, it's always part of something else. It doesn't just hang out as a thing by itself. So H2O2 is going to have a molecular weight that's twice this. So it would be 34 grams per mole. So if somebody tells you, here's the empirical formula, HO, but the molecular weight is 34, then what you do is you calculate what the empirical formula of your fragment is, the molecular weight of your fragment is, and then you divide it into the molecular weight of your whole thing. 34.00 divided by 17.00 is 2. And so that means that you would multiply the H by 2 and the O by 2, and that would be your final actual chemical formula. So let's go through a whole example of figuring out what the empirical formula was for a compound. So let's say that we have some information about the compound. We know that it is 81.7% carbon and 18.3% hydrogen. And this means that this compound is what we call a hydrocarbon. It's made of only hydrogen and carbon, and these are really commonly fuels. So all of those combustion reactions that I've been doing, where we've got some kind of a hydrocarbon like CH4 or C2H6 or C3H8 or however many they are. So all of these are different fuels. This one, methane, is our simplest one. This is the major component in natural gas. Some of the other alkanes you might recognize would be butane, which you find in lighters, propane, which you can find in a camp fuel. And of course, gasoline is a complex mixture of different hydrocarbons as well as some additional additives. So these are very familiar to us in terms of fuels that we use, but we don't necessarily know that much about them. So here is the information that we have. So when we are finding the empirical formula, this is our job. Our first step is going to be to make our lives easy for ourselves by choosing a sample that has exactly 100 grams. And the reason why we are doing that is because when we look at percentages, our percent adds up to 100, right? Because then we can say if we have 100 grams of sample, 81.7 grams of it will be carbon and 18.3 grams of it are going to be hydrogen. So we're going to choose a 100 gram sample and convert our percent into grams. So that's our first step. Now, anytime we are interested in getting some kind of a chemical formula, we know that these are based on moles, right? These are our mole ratios of the elements in that compound. So our next step is going to be to convert grams to moles using the atomic weight for each element. So if we have 81.7 grams of carbon, how many moles is that? Well, we know that 1 gram of carbon weighs, 1 mole of carbon weighs 12.011 grams. And that's from the periodic table, of course. And that 1 mole of hydrogen weighs 1.0079 grams. So pause the video and calculate these. You should get 6.80 moles of carbon and 18.2 moles of hydrogen. So that was our second step. The next step that we need is to calculate the simplest mole ratio. So this can have two parts, if necessary. Our part 1 is going to be dividing all of the moles by the smallest number of moles. That's what we do when we find ratios, right? So 6.80 moles of carbon is how many we have. We're going to divide that by the smallest number, which is 6.8 moles. And so we can see that's going to be 1, of course. And then we're going to take the other number, 18.2 moles of hydrogen, and divide it by 6.8 moles. And when you do this, you're going to get something like 2.67 hydrogens. And so this leads us to our second part of step 3, which is an if needed, find the least common multiple to give us integers. All right. We're interested in whole numbers. We don't have any kind of 0.67 of an atom of hydrogen, so that's not going to really work for us. We need these guys to be whole numbers. So when we look at this, hopefully you can recognize that 2 0.67 is about 2 2/3. I picked this one because it's one of the more complicated ones you might see. So when we find a least common multiple, this is a fraction, and it's equal to 8/3 if you multiply it out. And what we want to do is we want to get rid of that denominator. This will give us the integer. So to get rid of the denominator 3 down here, we need to multiply by 3. And if we multiply this one by 3, we need to multiply the other one by 3 because our ratio is 1 unit. All of our carbon scales with our hydrogen. So instead of 1 carbon, we now have 3 carbons. And instead of 8/3 hydrogen, we have 8 hydrogen. So this is going to give us our empirical formula. And I will say this step 2 is only needed some of the time. Often you'll just get integers from part 1 of this step 3. You don't usually need to do part 2, but I wanted to make sure that you saw how to do it in case you did need to do it. So that means that our empirical formula, our smallest, most simple relationship between these would be C3H8. So how would we know if this was the actual molecular formula? We would need to compare to the known molecular weight if there is one. So go ahead and calculate the molecular weight for C3H8. I got for my molecular weight here that it was 44.10 grams per mole, depending on how many significant digits you keep. So if we were told that the molecular weight is equal to 44.10 grams per mole, then we would know that the chemical formula would be the same as the empirical formula. Right? So it matches the empirical in this case. So it's also the chemical formula that C3H8 is. So let's think about a hypothetical. What if the molecular weight was really 88.19 grams per mole, we were told. So hopefully you can see that this molecular weight goes into this molecular weight twice. So that would mean that our chemical formula for this one would be twice our C3H8, so it would be C6H16. You would multiply each of these coefficients by 2 because our molecular weight is twice as big. Okay, so let's go ahead and try another example. This is one I want you to try without me working out the steps. So let's say that a sample is 24.27% carbon, 71.65% chlorine, and 4.07% hydrogen, all by mass. We want 2 questions to be answered. What is the empirical formula? And then in part 2, if the molecular weight is 98.96 grams per mole, then what is the chemical formula? So pause the video right now and try this problem out, and then we'll reconnect and check your work. Okay, so let's see how you did. In step 1, We assumed 100 grams and turned our percentages into grams. So we would have gotten 24.27 grams of carbon, 71.65 grams of chlorine, and 4.07 grams of hydrogen. So that would be our step 1. In our step 2, we're going to convert grams to moles. So you should have gotten 2.021 moles of carbon, also 2.021 moles of hydrogen, chlorine, and 4.04 moles of hydrogen. Now, the mole ratios here are nice and simple. So in step 3, we can see that when we divide 2 by 2, these guys are each going to have a carbon, and chlorine will be 1 to 1, and the hydrogen will be 2 to 1. So our empirical formula would be CClH2. So in our second part of our step, we're told that our molecular weight is 98.96. So we take this empirical formula and we calculate the molecular weight for just the CClH2. And this is equal to 49.48 grams per mole if you work it out. So now we can see that 98.96 grams per mole divided by 49.48 grams per mole is equal to 2. So that means our empirical formula was CClH2, and our chemical formula is C2Cl2H4. We take each of our coefficients and we multiply them by 2. So this is your process for calculating empirical formulas. What you need to calculate them are the mass percents of each element and a periodic table. If you want to know what the chemical formula is, then you would also need the molecular weight of the compound.